Wisconsin lakes using two forms of technology. And this is a project that is funded by the National Climate Adaptation Science Center of the USGS. So first, speaking on walleye fisheries in the ceded territory in northern Wisconsin, these are mixed fisheries comprised of a recreational and tribal component, and most of these fisheries are harvest oriented. Additionally, extensive stocking occurs throughout this region, even in lakes that have natural recruitment. Now, additionally, many of these lakes are fairly small at less than 200 hectares, and long-term recruitment declines have been noted in some of these lakes, while others maintain stable or even increasing populations. Now, these trends are likely influenced by climate change, but the exact mechanisms are unknown. Now, thinking about how walleye fisheries have changed in this region, managers have adopted this sort of resist, accept, direct framework for choosing how to deal with declining or stable walleye populations. Now, management strategies in this framework include resist, which is working towards maintaining a current state or returning to a historical state, direct strategies, which are actively managing towards a preferred state, and accept strategies, which are allowing the current state to change without management intervention. However, whether this RAD framework works depends on an understanding of the actual factors causing walleye recruitment declines. Now, thinking about what optimal walleye habitat is in an inland lake, I like to think of it along this continuum. So this is from Kitchell et al. 1977. And walleye are kind of like Goldilocks, where they occupy this middle stage of lake continuums, where we have eutrophic on the far end and oligotrophic on the other far end. Now, walleye prefer lakes with moderate water clarity and in cool water thermal regimes, and additionally, they prefer riverine systems with complex littoral structure. So lakes with those sorts of characteristics are deemed to be best for walleye. We can expand this a little bit further and think about water temperature and water clarity's influence on walleye fishery productivity. The first person to actually implement this sort of conceptual model was Lester et al. In 2004 with thermal optical habitat area, or TOHA. Essentially, TOHA consisted of 50% of the optimal growing temperatures thought to be experienced by walleye, which was 11 to 25 degrees Celsius, and 50% of the optimal foraging light intensity thought to be experienced by walleye, 8 to 68 lux. Now, we can think of TOA in lakes as existing in three parts, where we have optical habitat in one layer, thermal habitat in another, but where that overlap is optimal habitat or thermal optical habitat. Additionally, this has been pretty effective at describing fishery productivity in Minnesota, specifically on Mille Lacs, and more recently across the landscape in a recent publication. Now, switching back to thinking about northern Wisconsin, we have some pretty strong evidence that thermal habitat, at least in regards to this model, has shifted in northern Wisconsin. First, we have evidence that water temperatures have increased due to climate change, and this can cause context-dependent effects on walleye fisheries. So in some cases, temperatures within that 11 to 25 degrees Celsius range may increase in deeper or larger lakes, thereby providing more thermal habitat to walleye. But in some other lakes, specifically those smaller lakes in northern Wisconsin, increased temperatures above 25 degrees Celsius may increase in frequency in those smaller lakes or shallower lakes in general, and that would provide less thermal habitat in a system such as that. However, we also have evidence that optical habitat has shifted in northern Wisconsin due to water clarity increases in some ceded territory lakes. Now, overall, this would provide less optical habitat in most of these systems, and essentially this would decrease the availability of 8 to 68 lux throughout the water column, or additionally move 8 to 68 lux to deeper, therefore metabolically unfavorable water outside of TOA. I should also note that these increases in water clarity are a little less understood, such as the mechanisms are less understood, I should say. But it's likely reduced phosphorus loading or reduced erosion that has caused some of these shifts. Now, although we have pretty clear evidence that TOA has shifted, at least in regards to that conceptual model, there are still some major assumptions with the model lacking empirical support. First, we're not really sure if those model ranges, the 11 to 25 and 8 to 68, are truly optimal habitat. So those thermal and optical ranges were actually taken from laboratory studies and an observational angling study in the 70s and 80s. But additionally, the TOA model lacks information on oxygen, and this likely limits preferred habitat experienced by walleye as respiration is necessary for survival. Additionally, the TOA model lacks information on different sizes of walleye, and if it is to be related to recruitment or fishery production, this could be a pretty key component of the model that hasn't been assessed yet. So this brings up two pretty big research questions. First, is TOA an accurate reflection of optimal walleye habitat? And additionally, if it isn't quite accurate or could be improved, or I should say, if it isn't accurate, can that model be improved? Now, I'd like to highlight this previous evaluation of TOA that did occur prior to my study in 2006 by Brent Metcalf. And this thesis work found that walleye occupied thermal habitat, but not optical habitat when it was available in a lake. Additionally, this study found no selection for optical habitat, but it was slightly limited by its small sample size, sometimes including only 9 to 10 individuals, or detections, I should say, in a single time step. But additionally, this relied on non-continuous monitoring through radio telemetry. So these fish had to be actively tracked, and that may influence our interpretation of preferred walleye habitat. And that kind of brings me to our methods and using internal tags to evaluate TOA. So we deployed acoustic telemetry, which is a technology that relays signals from acoustic transmitters to acoustic receivers or stationary computers that can be placed throughout a lake. But additionally, we also used archival tags, which log information continuously over time, but require a physical recapture of an individual fish to get that data back. So with all of that being said, the objectives of my thesis research are to determine if walleye thermal and optical habitat occupancy varies among 3 northern Wisconsin lakes in relation to season and total length. My second objective is to determine if thermal and optical habitat boundaries employed in previous research are occupied by walleye. My third objective is to redefine optimal walleye habitat using direct measurements of temperature, light, and dissolved oxygen occupancy. And my fourth and final objective, related to those two tagging technologies, is to determine if data resolution and cost effectiveness differs between two tags used to monitor walleye temperature occupancy. And with that, I'll speak a little bit on my methods, specifically walleye sampling and tagging that occurred for this project. So first, our study lakes, Escanaba, Sparkling, and McDermott, were located in the ceded territory in northern Wisconsin, represented by this yellow line here. So 2 of our lakes, Escanaba and Sparkling, are in Vilas County, and one of our lakes, McDermott, is in Iron County. Speaking on the lake characteristics a little bit more, Escanaba was our largest lake, and it's a drainage lake. It also has a maximum depth of 8.8 meters and a mean secchi depth of 3.1 meters, so moderate water clarity. And this is a sustained recruitment lake that hasn't been stocked since the 50s or 60s, a very long time. This lake is entirely sustained by natural recruitment. Now, in contrast to this lake, we have McDermott and Sparkling, which both have declining recruitment and are currently stocked with extended growth fingerlings. But other than that, these 2 lakes are much different from each other. So McDermott is a drained lake that is 33 hectares, our smallest lake in this study, and it also has a maximum depth of 5.8 meters and a moderate water clarity at 3.2 meters. Sparkling, on the other hand, is a seepage lake. It's kind of a middle-sized lake at 64 hectares. And has a maximum depth of 20 meters and a mean secchi depth of 5.1 meters. So this lake is much clearer and more alekotrophic than our other 2 lakes. The tags we used in this study included a StarID DST Micro TD, which is an archival tag that records a temperature and depth observation simultaneously. We deployed 122 of these tags, and they lasted 355 days until their memory was completely filled. So this programming interval, I actually set them to record at this rate so we could maximize the amount of information that was collected during the summer or the field season where TOA actually existed in our lakes. So when 11 to 25 degrees Celsius was available. And these recorded every 8 minutes during that time frame, and then switched to every 20 minutes during fall turnover. Now, additionally, we used acoustic transmitters that were made by Innovasi, and these were V7TP4Xs. We deployed 40 of these, and they lasted 365 days until their battery completely expired. These sent a single temperature observation every 2.6 to 4.3 minutes at uniquely coded intervals, but they would switch to a depth observation and then back to a temperature within those time frames. So this was not a paired observation like the archival tag. Additionally, I should mention these tags were both similar sizes, and both tags, if it wasn't clear, record temperature and pressure, which is a surrogate for depth. Additionally, we deployed more archival tags because these need to be physically recaptured, and we needed more out in our lakes to have a better chance at recovering them from individual fish. Now, we collected walleye during adult population estimates that occur on each of our lakes in the ceded territory. This is a standardized procedure, and we used fike nets to collect our fish during the spawning run. Now, because fish were being marked during the fike netting portion of this, we also had to go back and try and recollect fish during a recapture run that consisted of night electrofishing, and this provided an additional opportunity to recollect more fish that hadn't been tagged yet. Generally, when fish were caught during these surveys, they'd be brought back to the boat launch and then moved to these holding tanks, which were large, covered, and had recirculating water and aeration. Fish that were sorted and then subsequently chosen for surgery would be moved to these pre-surgery tanks near a surgery station and table, usually only a few individuals at a time. Then after surgery, those fish would be moved to recovery tanks, monitored for a brief period of time, and then released in the center of the lake via a boat. I should also mention that we use this sort of approach to maximize space and limit crowding. So usually I show a video here, but because we're on Zoom, I thought this would be more effective. So tag implantation usually consisted of taking a fish from that pre-surgery tank and moving it to a wet foam insert covered with cabinet liner. And on that insert, the fish would be immobilized using a TENS unit, which provides an electrical pulse that essentially stuns the fish. Additionally, we would use a recirculating water pump during surgery, and this would provide water to the gills so the fish could respire as this was occurring. So essentially, an incision would be made in the body cavity, and then a tag would be inserted through that incision, and the incision would be closed using monofilament suture. Additionally, I should mention right now that we tried to equally distribute our tags among 3 different length categories: a small, a medium, and a large. But also we kind of relied on what our nets caught, and sometimes we weren't able to be as choosy as we might have wanted to. Additionally, after these surgeries were completed, these fish were monitored briefly before being released. And here's an example of a fish that was recaptured a couple days later. And we can see that tag is sutured into place and actually has an external filament, which I'll talk about next. So, of course, to identify these fish with internal tags, we need some sort of external marker for anglers to identify these fish, but also for agency personnel. So for our fish with acoustic transmitters, we used a T-bar anchor tag on the dorsal side of the fish, shown here. But our fish with archival tags actually had a built-in external filament, which we refer to as a noodle tag, and that protruded from the body cavity and was anchored into place, again, for identification of those fish. And this is how many fish we tagged during 2022 in total. So we tagged 91 fish in Escanaba Lake, 21 in McDermott, and 64 in Sparkling. I should note that 21 fish doesn't seem like a lot, but this is about 30 to 60% of our current adult population estimate for 2022. Additionally, because that population size was so small, we only deployed archival tags in McDermott Lake and chose not to deploy acoustic transmitters or receivers there. Additionally, those extra tags were put into Escanaba Lake as there are more fish there. Therefore, it was easier to catch extra fish for tagging. Additionally, we had to characterize TOA in these lakes, and we did that using these light and temperature logger deployments that were also outfitted with acoustic receivers. So going over this quickly, most of these consisted of an anchor connected to galvanized steel cable, and spaced throughout that cable at different depth intervals were hobo pendant light and temperature loggers that were actually extended a little bit from the cable to limit shading. And they were also placed kind of at alternating intervals as well, so that they wouldn't overlap each other, if that makes sense. So these record temperature and light every 10 minutes throughout the summer. And I should also note that we attached acoustic receivers to these deployments because we need to collect that information from those acoustic transmitters. These are the deployment locations of those acoustic receivers and light and temperature logger deployments. First, to kind of orient you to this map, our figure here has loggers only, represented by white triangles, and only on McDermott Lake because there was no acoustic transmitters there. We also have receivers represented by white circles, and receivers and loggers represented by black triangles. So essentially, when we deployed these acoustic receivers, we tried to space them to maximize detections based on our expectation of detection probability. And essentially what that means was covering a variety of habitat types and also potential pathways fish would move through. Additionally, we tried to deploy those light logger strands in the deepest section of the lake. So we had 3 in Escanaba, kind of going over the deepest area, 2 in McDermott, and 1 in Sparkling. So these secondary ones kind of provided a duplicate in case one was lost or damaged. And we didn't do that in Sparkling Lake because there's actually a UW-Madison raft here collecting additional data as well. So fast forward to May of 2023, and we had to recapture those fish with archival tags to get that data back, of course. So doing so, we decided to do surgical removals instead of dispatching the fish. The reason being that we thought this would be better for anglers by retaining that fish in those lakes. And additionally, this hadn't been done before as far as I'm aware, at least with walleye. So this was kind of an interesting case study to test this. So these surgeries, or surgical removals, I should say, followed similar methods as the surgeries, where the fish was placed in a foam insert, given water, irrigated gills during surgery, and then the tag, an incision was made, the tag was removed, and that was sutured with monofilament suture. We had really good survival with this, with no signs of acute mortality, and we were even able to recapture fish over a month later, which indicated long-term survival was possible. So again, this is a novel procedure that, as far as I'm aware, hasn't really been done before in this kind of system. Now, additionally, we did recapture some fish with acoustic transmitters during this time frame. And during those instances, that fish was measured, sexed if possible, and then released immediately. So here's an example of one of those acoustic transmitter fish, and you can barely see that incision and surgery scar, but there it is. And again, that fish was identified with a T-bar anchor tag. Now, speaking on the distribution of walleye that I used in my analysis, we have 50 fish from Escanaba, 5 from McDermott, and 33 from Sparkling. Again, 5 doesn't sound like that many, but that's a 24% recapture rate based on our adult population, or based on how many fish were tagged. And again, that adult population estimate is very small, so it still came out as a decent number. Additionally, when looking at a recapture rate for archival tags from May to May, 1 year, we had 41% recapture rate on Escanaba, 24% on McDermott, and 36% on Sparkling. So these are really high recapture rates. We were expecting something maybe along the lines of 20, but we did really good at getting these archival tags back. Now, thinking about this in terms of those size categories that we're using in analysis, we had pretty good distribution in Escanaba, okay in McDermott, but again, not many fish recaptured, so we kind of got what we got, but our size was definitely skewed towards larger females in Sparkling Lake. Now, some additional things we did for this study for quality control included this list here, and I'm just going to cover them briefly, just in the interest of time. So some things we included in this thesis were an acoustic receiver range test on each of our lakes. Additionally, mobile acoustic receiver surveys to determine if walleye had died or shed their tag outside of the stationary receivers. Additionally, we did some temperature and depth sensor validations with our acoustic transmitters and archival tags to determine precision. And additionally, we had to determine the mortality or tag shedding events that occurred for fish with acoustic transmitters. Now, moving into my analysis and results, first, I'd like to talk about how we interpolated light intensity from a walleye depth value from a sensor. So at every 10-minute time step in each of our lakes, I would construct a curve that looks something like this. And the first thing that would be done is I would use a polynomial to estimate surface light intensity. And that would look something like this. So at 0 meters, or the surface, a light intensity would fall around 6,000 lux in this case. Now, for the max depth at each of these time steps, it was always 0 lux, regardless of time of day or lake. So consistently, we would set our maximum depth at 0 lux. Now, this provides this continuous curve, which we're able to use linear interpolation to get an approximate light intensity experienced by a walleye, and that would look something like this. So if that fish was at 1 meter deep, it would be at about 3,000 lux at this specific window of time. We also did this with dissolved oxygen, but those were measured weekly and not at every 10-minute time step, because we went out in the field and did that, or used supplemental data collected by the CFL or Wisconsin DNR. Additionally, we actually measured the zero value, so we didn't use any methods to interpolate or estimate that. Now, speaking on objective one, to remind everyone, that was to determine if walleye thermal and optical habitat occupancy varies among 3 northern Wisconsin lakes in relation to season and total length. And I chose to evaluate this objective during June to October, so June 1st to October 31st, because these were dates where TOHA existed in our lakes in some capacity. So I structured this analysis within a generalized additive mixed model, or a GAM, and essentially I constructed 3 final models, one for temperature, depth, and then one for light intensity, and these were all grouped by individual fish and day of year, or date. These models also contain smooth components, as they are a GAM, and those smooth components consisted of day of year, which was a cyclic smooth, and Walleye ID, which was a random effects smooth. Additionally, this data is highly autocorrelated, and we used a grouped autoregressive structure to help deal with that, and we selected our best performing models using AIC criterion. Additionally, I'd like to cover our candidate models real quick, and this is what we use to test which best explained habitat use, or occupancy, I should say, in each of these lakes. So first, we had the additive effects of lake, total length category, and our smooths. We had an additional model, which was just lake plus the additive effects of the smooths, total length category plus the additive effects of the smooths alone. And then we also tested this 5th model, which was an interaction between lake and day with a tensor interaction, also fitted with the additive effects of those smooths. The idea here being that when we plotted this, we thought it might be an interaction that existed for depth and light intensity models, but we did not test this for temperature because it did not appear to exist. So first, starting with temperature occupancy, we found that it varied by lake, total length category, and day. So starting with this figure on the left here, we have day of year on the x-axis and predicted temperature on the y, and each of these colored lines represents a lake. So we found that in each lake, walleye use significantly different temperatures, albeit marginally by on average about 0.5 degrees Celsius. So in McDermott Lake, those fish were in slightly warmer water than Escanaba, and in Sparkling Lake, those fish were in slightly colder water than Escanaba. Additionally, fish in McDermott and Sparkling Lake used significantly different temperatures. I should also note that the smooth was significant for day, and it was a pretty similar synchronous movement into this warmer temperature that peaked around July and then declined slowly as fall turnover occurred. So going into October here. Again, this pattern was similar among all lakes. Additionally, Walleye ID was significant but is not shown here. Additionally, we found that total length category was significant, albeit marginally. So we have our total length category on our x-axis, small, medium, and large, and also predicted temperature again on the y. And we found that small and medium-sized fish use similar temperatures, or non-significantly different, I should say. And those medium and large fish, same story, non-significant. However, small and large fish use significantly different temperatures by about 0.5 degree Celsius. Now, moving on to depth, we found that this varied by lake and an interaction between lake and day. So in McDermott and Escanaba Lake, these fish use similar depths as shown on the y-axis, but fish in Sparkling Lake were on average deeper. Additionally, we found that fish in Sparkling Lake moved deeper over time, or time of year, going deeper in the fall as turnover occurred, where that was not noticed in McDermott or Escanaba lakes. Additionally, this model excluded walleye ID as a random effect to improve model fit. And you may be asking, what does this have to do with TOA? But the big takeaway here is that walleye and sparkling lake were deeper, and this might indicate that these fish are going deeper to maybe occupy a different light intensity. So moving on to our next plot here, we have light occupancy, and we found that this was poorly predicted by lake and total length category. So first, before I walk through this figure, I should note that these values were square root transformed due to an exponential skew, and they're back transformed in this plot. So we found that day was the most significant predictor, only significant predictor, I should say, of light intensity used throughout the time frame. As you can see, it's pretty stable, but there's this slight dip in the middle of summer, and I think this is due to greater periphyton accumulation that occurred during this period. So even while we cleaned loggers, it seemed to occur at a faster rate during this time. But then light intensity declined as October approached. And again, that's because day length got shorter, but fish in sparkling were also deeper. Additionally, I left the raw data in here just to show how much of a shotgun blast it truly is. Additionally, walleye ID was significant but is not plotted. Now, moving on from there, we found that temperature used was pretty similar and light occupancy was also pretty similar, albeit not significantly explained. Therefore, our next objective is to determine if those thermal and optical habitat boundaries employed in previous research are occupied by walleye to test if that TOA conceptual model, those habitats are used. This time frame was the same as our previous analysis. However, we calculated those occupancy rates in thermal and optical habitat when those habitats were available in each lake during that time frame. So this provided 1.3 million temperature observations to pull from and 840,000 light observations to pull from. I should note that this analysis excludes night, therefore there's much less light observations used in this analysis. So first, starting with thermal habitat, we found that thermal habitat occupancy was very high. So calculated over all fish, it was 95%. And by individual, it ranged from 79 to 100% of the time being in 11 to 25 degrees Celsius. Additionally, a very low CV or coefficient of variation indicating that most of these fish were just generally within thermal habitat. Now, when thinking about optical habitat, however, we found that only 6% of the time fish were actually in it when it was available. And by individual, that ranged from 0 to 15%. And overall, our CV was pretty low at 37.1%. So this indicates, again, that for optical habitat, or 8 to 68 lux, fish just generally weren't in it. Now, breaking this down by some other categorizations, we found that regardless of categorization, occupancy and thermal habitat was relatively high. So in each lake, fish were in it a majority of the time, albeit slightly less often in McDermott Lake. By month, we found that occupancy was similarly high, although it declined in October, and that sort of makes sense as that habitat becomes more constricted due to fall turnover. Additionally, when breaking this down by time of day, we found that there was low variation in thermal habitat occupancy. However, fish were in thermal habitat a little more often during the day than at night. Additionally, we decided to analyze this for optical habitat, and we found that regardless of lake, fish were generally not in 8 to 68 lux, albeit they were outside of it slightly more often in McDermott Lake. Additionally, we found that by month, occupancy was similarly low, but increased slightly in October, or I should say doubled in October. Still low, but again, average light intensity declined during that time, so kind of makes sense that they were more likely to be in it. Now, the major takeaway here is that occupancy varied a lot by time of day. So at dawn, 23.2% of observations were in it. Day, 3.3% of observations. And then at dusk, 26.2% of observations. Now, there is no optical habitat at night, so these fish couldn't be in it, even if they wanted to. I just left that in there to kind of signify that there was no optical habitat at night. We can break this down by thinking about where 8 to 68 lux actually occurs based on time of day. So during dawn and dusk, among all of our lakes, as shown here on the x-axis, time of day, optical habitat was shallower and overlapped with walleye depth in each of our lakes. So in Escanaba, pretty shallow at about 1 to 2 meters. Also in McDermott, kind of the same story, 1.5 meters, about 1.5 to 2 meters. And then in Sparkling Lake, 4 to 5 meters. Now, when thinking about where optical habitat occurs during the day, it was on average much deeper and in water that was unoccupied by walleye. So in Escanaba, 4 to 6 meters, in McDermott, 5 meters-ish, and then in Sparkling Lake, 10 to 15 meters. Now, to highlight why these habitats may have been unoccupied, it could be due to low DO, as that occurs in Escanaba and McDermott lakes around this depth. But additionally, in Sparkling Lake, DO wasn't an issue, but this water is much colder and may not be preferably occupied. Again, no optical habitat at night, so it's not shown. So we can use this kind of conceptual diagram I made to kind of think about where thermal and optical habitat are occurring in each of our lakes. And this is sort of the picture we get here. So just showing you what we've already talked about, but simplified and plotted out. Fish in Escanaba Lake were generally shallow in 11 to 25 degrees Celsius, but were not in 8 to 68 lux, and again, that occurred in low dissolved oxygen water. Now in Sparkling Lake, fish were generally in 11 to 25 degrees Celsius, albeit deeper on average than our other two lakes. However, they were not in 8 to 68 lux, which occurred in colder water. Additionally, in McDermott Lake, it was pretty similar to Escanaba, where fish were generally in 11 to 25 degrees Celsius, but not in 8 to 68 lux because of low dissolved oxygen. So this is kind of the big snapshot picture we get from the summer of 2022. Now, moving forward, we see that 8 to 68 lux might not be the most accurate predictor of optimal walleye habitat, and therefore we sought to redefine optimal walleye habitat using direct measurements of temperature and light and dissolved oxygen. Occupancy, excuse me. So we analyzed data for this objective from June 15th to August 31st of 2022, as this represented the period of greatest stratification among our lakes and therefore the greatest availability of different temperatures for walleye to select from. Additionally, we only retained walleye with greater than or equal to 15 days of data for this analysis, just so it wouldn't skew our interpretation of preferred habitat by having fewer observations. Now, the way we calculated preferred habitat was based on these three independent metrics, the first of which is pretty simple and just is a summary statistic, specifically a mean and median. So we calculated a mean and a median for each individual, but what I'll report is actually a mean of our means and a mean of our medians. The reason for this being that this helps characterize some of the variability that we were seeing among individual fish by allowing us to plot standard error. Additionally, we used ecological niches as described by Magnuson et al. In 1990. So specifically, we focused on the narrow niche method he described then, which is the middle 66% of observations that occur within a data set. And we also calculated this by individual and reported it as a mean, again, to kind of get at that individual variability component. Additionally, I calculated habitat selection ratios using methods described in Pierce et al. 2013. I won't dig into the math on this, but essentially, it's pretty simple, and this just looks at the number of observations of a fish in a particular habitat related to its availability and the total observations for that fish. So this was originally designed for coarse habitat, I guess you could say, so like substrate type or something along that nature. However, it has been used for temperatures such as this study, and we thought we would try and apply it to light occupancy and dissolved oxygen as well. So starting with temperature, we found that walleye were generally in this range of temperature based on our first two methods. So to orient you to the graphs I'll be showing, we'll have our value on the x-axis, in this case temperature, and then occupancy rate on the y-axis. And this is based on the total number of observations. So generally, fish, or I should say our mean was 20.9 degrees Celsius, so somewhere around here, and our median was 22.3 degrees Celsius, somewhere around here. And our lower and upper narrow niche range was 20.5 to 23.2 degrees Celsius, So that means between these two white lines, which are represented by these numbers, 66% of our observations fell here. Now, when thinking about this for light intensity, I should again note this data is exponentially skewed. Our mean was 4,227 lux, our median 2,603 lux, and those narrow niche boundaries were 504 or 584 lux to 8,503 lux. So 66% of our middle observations fell somewhere in this range. Now, when calculating this for dissolved oxygen, we found that our mean was 7.9 milligrams per liter, our median 7.8, so around the same area. And additionally, we found that 66% of our observations fell between 7.4 milligrams per liter and 8.5 milligrams per liter. Now, speaking on habitat selection ratios, that third metric I spoke on, I'll cover this graph real quickly in the same manner. So on our x-axis, we have a mean selection ratio. This dashed line represents 1. Between 0 and 1 indicates that it's not preferred or avoided, and a greater than 1 value indicates it is preferred or it's selected for. And we also broke these down by different bins. So for temperature, this is 1 degree Celsius bins, and we found that 21 to 23 degrees Celsius was the most preferred. Fish selected for this the most, especially based on its availability. Additionally, we found some avoidance actually for greater than or equal 24 degrees Celsius and less than 16 degrees Celsius. When calculating this for light intensity, this didn't work too well, and I'll kind of explain in detail why that is. So we have, again, the mean selection ratio on the x-axis and light intensity bins broken into the 1,000 on the y-axis. And we found that 3 to 5,000 lux is maybe the most preferred, but we also get this really weird curve that's U-shaped, and it seems like the standard error increased a lot as light intensity increased as well. Additionally, we did find that less than 1,000 lux was avoided, or less than, 1,000 lux was avoided. So I wasn't really satisfied with this sort of U-shaped curve we got, and I tried to recalculate light selection ratios during October to November, or in other terms, when water temperature was less than 16 degrees Celsius and they couldn't really select for optimal temperatures. But additionally, I tried to calculate this when walleye were already in 20 to 23 degrees Celsius, which appeared to be preferred. Now, neither of these indicated a preferred light range when I recalculated these metrics, and they resulted in a similar U-shaped curve that I showed earlier. So both of those are not reported. Now, last, I also calculated this for dissolved oxygen, and we found pretty overwhelmingly that greater than or equal to 7 milligram per liter was preferred. And again, we broke this down in 1 milligram per liter bins. But I should also note I cut this off at less than 9 milligrams per liter because that saturation level was pretty limited in McDermott and Escanaba Lake. Therefore, they couldn't select for it just because it didn't exist. Now, moving away from TOA, I'd like to cover our tag analysis real quick, which was to determine if data resolution and cost effectiveness differs between two tags used to monitor walleye temperature occupancy. For this analysis, we excluded McDermott Lake and 2 speared walleye that we did not recover tags. And this included temperature sensor values only because we would get duplicate results by using the depth sensor observation. So what I mean by that is if a tag collected 5,000 temperature observations, it probably collected 5,000 depth observations as well, or close to it. And we used 38 acoustic transmitters in this analysis and 48 archival tags. The things I'll be covering for this analysis are the number of individual fish providing data relative to the number of tags released, the mean number of temperature observations obtained from an individual fish, the average time interval or average time elapsed between 2 subsequent observations, the total effort expended to collect and recover data reported in hours, and also the total cost to obtain data, including that effort cost. Now, starting with the first of these, the number of individuals providing data, from the total number of implanted tags, 38 of 38 or 100% of our acoustic transmitters were detected at least once, and 15 of those 38s had at least one observation per day. Now, for archival tags, of the total 115 we implanted, 42% had recovered data. 40% of the data from those tags was viable and could be used in analysis, and 28%, or 32 of 115, had at least one observation per day. So, relatively speaking, we got more daily information from acoustic transmitters than archival tags. Now, thinking about the mean number of observations per tag type, archival tags reported significantly more temperature observations on average than acoustic transmitters. Just to cover this real quickly, on average, 20.6 thousand temperature observations for archival tags, while only 7.9 thousand for acoustic transmitters. However, I should note that the max for each tag type was pretty similar, around 26,000 each. And additionally, there are some zero values included here because I included failed tags. Now, when looking at the mean time elapsed between two consecutive observations, we found that archival tags recorded significantly faster than acoustic transmitters on average by individual. This is just, this p-value represents an analysis just by tag type, but I applied this by lake to kind of show the variability here. So for acoustic transmitters in Escanaba Lake, on average, they sent an observation every 30.3 minutes with a super high standard deviation. And this is mostly driven by a few individuals. At some points, fish were not detected for over 30 days on end, and then they reappeared on the grid. Now, when thinking about Sparkling Lake, we detected fish more frequently on average, actually at half the time on average, and the standard deviation was much lower. Any fish that went off grid did not do so for quite as long. Additionally, archival tags in each lakes were set to record in 8-minute intervals, so there's low variation associated with that. Now, speaking on total effort, we found that archival tags required much more effort to implement than acoustic transmitters. So in these lakes, we had an estimated 191 hours of effort for archival tags, but only 90 hours of effort for acoustic telemetry, I should say. So for acoustic telemetry, that was consisting of receiver maintenance and fike netting for the initial tagging of those fish. But for the archival tags, we had the tag offloads taking some time, but not much. That tag initialization and fike netting for implantation taking a similar chunk of time as the acoustic telemetry, but it was the recapture effort that required many more man hours than acoustic telemetry. So this is driven, of course, by that recapture event that needs to occur. Now, regardless of that recapture event, we found that archival tags cost less overall when compared to acoustic telemetry. And that's mostly because the upfront cost of equipment was much greater for acoustic telemetry. Specifically, those receivers and transmitters were more expensive. Now, thinking about the mean cost per individual tag with recovered data, we got about $1.1 thousand for archival tags and $1.3 thousand for acoustic transmitters. Additionally, when thinking about this as a mean cost per observation using continuous observations, we found that archival tags were $2 a pop and acoustic transmitters were about 6.5. Now with that, I'll be moving into my discussion. So first, speaking on that tag overview or analysis, I should say, because it's fresh in our minds, we found that archival tags collected more temperature data for less cost during that time frame. However, those results were largely dependent on multiple factors used in this analysis. First, I used a continuous monitoring interval, not like an hourly average or a daily average. And I'd argue these are probably more important for fisheries managers or researchers. So these could definitely skew our interpretation of which is more effective at recording this type of data. Now, additionally, our recovery rates for archival tags were exceedingly high. So in other systems, maybe we'd expect lower or moderate recovery rates, and that would influence our cost efficiency as well. Additionally, the time frame of our project, so we were only looking at May to October of 2022, essentially one field season. But if this was extended to another year or multiple years, that would definitely influence our interpretation as well. And now that effort cost, that varies widely. But again, I calculated that based on my salary. So I'm pretty cheap. So I would take that estimate with a grain of salt. but that relative answer, right, the one being more cost effective than the other, that is still correct. Now, we're working on a tagging manuscript that addresses all of this in greater detail. So just a brief overview on that here. Now, moving back to TOHA, we saw that temperature occupancy varied by lake and total length category among our lakes, but those predicted differences were small at about half a degree Celsius. Now, additionally, lake thermal regimes vary, so it's not surprising that walleye within different lakes occupy slightly different temperatures based on their availability. Additionally, we did find a slight difference in size specifically between large and small fish. But I'd like to mention that we were only able to tag fish greater than or equal to 310 millimeters, and fish smaller than that may have different habitat requirements than adults, therefore actually providing a more significant relationship. So that's something that could be explored in the future. Now, when thinking about depth occupancy, we found that on average it varied by lake, but not total length category. And this kind of gave us an idea that maybe these fish in sparkling lake are moving deeper to be in a different light level. When looking at light occupancy, we found that it was not explained by lake or total length category, and it was best explained by day of year or season. And that makes sense as light declines seasonally, especially in the northern hemisphere. So moving on and thinking about our second objective, redefine or uh, categorizing what fish were in thermal habitat and what fish were in optical habitat, we found that occupancy rates were high and consistent in thermal habitat, and we did note that fish were sometimes outside of it, but it wasn't very common. And fish were outside in warmer water when it was limited in shallow water. So when 25 degrees Celsius became limited in shallow water, we saw fish start to peak above it. Additionally, when temperatures were available within that range, we did see fish go into colder water for brief periods of time. Now, thinking about optical habitat, we found that this was varied a lot by time of day, and fish were generally not in it regardless. Additionally, we found that occupancy increased when this became more available in shallow water. And that kind of brings up this important note to make that this could still be optimal foraging habitat as originally described, but it's clearly limited by hypoxia, and metabolic preferences may take priority over seeking this out. And additionally, I guess you could say the habitat sort of comes to them at dawn and dusk. So that optimal foraging habitat might be available for a brief window in each lake where they're able to exploit it. Now, thinking about our third objective, redefining TOA, we found that 20 to 23 degrees Celsius was the most preferred across all the metrics I used to calculate this. And this was actually reported as an optimum by Hokanson in 1977. Additionally, we found that temperatures greater than 24 degrees Celsius and less than 16 degrees Celsius were avoided when available, which indicates that the original TOA model might be too broad. Additionally, for our light metrics, we found no clear consensus of a preferred light range, and that habitat selection ratios additionally might not be good at characterizing this, specifically because the availability of light available in a lake is very dynamic. So it changes a lot within a day and temporally. So it might not be a good way to categorize that. Last, we found that dissolved oxygen levels greater than 7 milligrams per liter were preferred, and that was among metrics as well. Now, one thing I'd like to highlight before I end this is that a potential flaw in our light categorization is that we use pelagic values to interpolate all of our values of walleye light intensity, even when they were in shallow water. So in this plot here, we have time of day on the x-axis and light intensity on the y. And the big takeaway here is that our scales are much different. So 30,000 lux at a max on average in Escanaba Lake, while in the littoral zone, 16,000 lux at a max. So just indicating that there's a stark contrast in light intensity within a lake at the same time of day. And this kind of brings up an interesting question of whether TOA exists in pockets or little sections within a lake, right? So maybe there's TOA in a back bay somewhere, but it's not in the pelagic zone, and we weren't able to characterize that. But also, this brings up an interesting question of within TOA models, should that benthic habitat area that's been traditionally used be switched to a volumetric estimate, or maybe just an estimate that includes the littoral zone, as this might have a better description for optimal walleye habitat in those lakes? And in part, some of this is being answered by a current postdoc at UW-Madison. Now, I'd like to end this by empirically defining thermal, optical, or oxy habitat area for walleye. Right now, we have strong evidence that 20 to 23 degrees Celsius is preferred and that oxygen levels greater than or equal to 7 milligrams per liter are preferred. Additionally, I kind of recommend substituting light intensity with water clarity, specifically Secchi depth for now, as previous modeling independently came to conclusions that 1 to 3 meters is an optimal for walleye, and it's easy to collect in the field and estimate, and it's much less volatile than raw light intensity values. Now, additionally, this range that I just described requires validation, specifically whether it can predict or correlate to walleye production and abundance well. Now, in future research, I hope to see something along these lines provided or applied to identify walleye bright spots or lakes that can maintain walleye in a changing climate, or maybe have an abundance of some sort of habitat that's considered optimum for walleye. And of course, this could be an additional tool for RAD management for walleye in Wisconsin. Now, with that, I'd like to thank everyone for helping me with this, specifically my graduate committee, Dr. Dan Iserman, Dr. Dan Demkowski, Dr. Josh Robbie, Dr. Stephanie Shaw, Dr. Olaf Jensen, and of course, Dr. Lisa Izzo. I'd also like to thank my funders, the USGS National Climate Adaptation Science Center, as well as the Wisconsin DNR, especially at the Escanaba Lake Research Station, for all their help and support. Additionally, staff and graduate students at UW-Stevens Point, and of course, staff and researchers at UW-Madison, both for the Center of Limnology staff who helped with field sampling and analysis, but also Kemp Natural Resources Station who housed me through the field season. Additionally, I'd like to thank the Sheboygan Walleye Club for some additional funding. And there's many people who helped make this project possible, and to them, I want to thank them as well. And that is all I have.
All right, so I think we have time for a couple questions. If people want to use their raise hand option, I'll allow you to unmute if there are any questions. If I can see you, there's a lot of you. A little bit of chatter. Greg's congratulating you there in the. So Logan Cutler asked, did you have any angler harvest of tagged fish?
Yeah, for sure. Thanks for asking, Logan. So didn't cover that, but we did have angler harvest of tagged fish, specifically in Escanaba. So that lake was closed to harvest for, I believe, about 20 years, maybe 19, and then it was opened on June 15th of 2022. So we had an influx of fish that were harvested during that time. In instances where that occurred with those archival tags, they had data offloaded. Well, first I should mention they were collected by the staff at Escanaba Lake. And once those, I picked up those tags, I offload data from them and held them until we were able to re-implant them in more fish, generally in Escanaba Lake. But we also re-implanted some in McDermott Lake. So yeah, thanks for asking.
Yeah, and also some fish came back from tribal spears who have mandatory reporting. So the folks that were at the creel stations, the Glyphwick folks, helped us to get those tags back.
Yep.
All right. For those of you that are actually part of Ben's committee, you have another Zoom link that you can rejoin. We'll take like a 5-minute break here and then everybody can rejoin. But thanks to everybody who showed up today. I did record it. So if somebody wants a copy of it, feel free to reach out to me and I can arrange for you to get access to it.